Okay, for this lesson I'm going to present on a topic called logarithmic differentiation, which makes it simpler to find derivatives when you have a lot of products and quotients and functions inside functions and so on all together in one problem. For example, with example 1, we could find the derivative of this directly, but we do have a product, so it would take a product, would require the product rule to do the derivative of the top, and it would require the quotient rule to take care of the fraction, and then we would also have the chain rule because we have 7x minus 14 underneath the radical. And so we'd have product rule, chain rule, and quotient rule all going on in the same problem. So we could do it, but here's another alternative. It's called logarithmic differentiation. So whenever you have a lot of products, quotients, and or functions inside functions in the same problem, you can try this. Try taking the natural log of both sides. So we'd have natural log of y is equal to the natural log of x squared, square root 7x minus 14. In fact, I'm going to rewrite that as 7x minus 14 to the 1/2 power over 1 plus x squared. Now, by properties of logarithms, when you studied logarithms, you learned things like the log of a times b is the log of a plus the log of b. And you learned that the natural log of a over b is the natural log of a minus the natural log of b. And you learned that the natural log of a to the x A. So we can apply all three of those properties to this problem to rewrite the right side as the natural log of x squared plus the natural log of 7x minus 14 to the 1/2 power minus the natural log of 1 plus x squared. And then we can even simplify one step further. By bringing the exponents down in front, I get 2 natural log of x. And here, bring the 1/2 in front, I get 1/2 natural log of 7x minus 14. And then this one we can just leave as is. There's nothing else I can do to simplify that one. Okay? Now, we haven't taken any derivatives yet. All we did is rewrite the problem in a manner that'll be a little bit easier to calculate the derivative. Now, taking the derivative of both sides with respect to x, we get 1 over y times the derivative of the inside dy dx equals 2 times 1 over x plus 7/2 1 over 7x minus 14 minus 2x over 1 over 1 plus x squared, or 2x over 1 plus x squared. And now we're trying to find dy dx, so we can multiply both sides by y. dy dx equals y times 2 over x plus 7 over 2 times 7x minus 14 minus 2x over 1 plus x squared. And we can be done there, or we can realize that all we have to do to finish this is substitute what y really is. So take the original expression we were given for y and put that in place of y. And now we have x squared square root 7x minus 14 over 1 plus x squared times the expression in parentheses 2 over x plus 7 over 2 7x minus 14 minus 2x over 1 plus x squared. So again, this derivative could have been calculated directly, but might have been more complicated. This by taking the natural log of both sides, we have a big long expression, but all the derivatives that we calculated were pretty easy. We had the derivative of natural log x here, derivative of natural log of 7x minus 14, and the derivative of 1 plus x squared, which were pretty easy derivatives to evaluate. Okay, go ahead and pause your player and try example 2 on your own. And after you're done, go ahead and press play and see how you did. Notice on this problem, y equals x to the x, we really don't have any other methods that would work for this problem. We can't apply the power rule because the power is not a constant. And we can't apply the exponential rule, like e to the x, because the base is not a constant. So the only option we have is to use logarithmic differentiation. So we'll start off by taking the natural log of both sides. And then we can rewrite that as x natural log x. And now we're ready to take the derivative of both sides. So the derivative of the left side with respect to x would be 1 over y, dy dx, and then using the product rule, we get 1 times natural log x plus x times the derivative of natural log, which is 1 over x. And now we can solve for dy dx by multiplying both sides by y. And that could also be written as x to the x times natural log x plus 1, filling in the original y in place of that y. And again, that's the only way we could find the derivative for this particular function. Anytime you have an x in the base and in the exponent position, logarithmic differentiation is the only way that you can find the derivative. So, for example, if we had sine x in the exponent, logarithmic differentiation is your only option. And that completes the notes for section 3.9 and logarithmic differentiation.